Hi, this is Ben Goodrich, and today I will be going over the section notes that I created for the section last Friday. These, if you were in the Monday section and couldn't make it due to the snow cancellation, can follow along uh, with me today. This file is available on Courseworks under Files and Resources, and then the folder for section material. You should download this file now so that you can follow along and do the R exercises. So this file is an RMD file, which is a file format created by RStudio for making and displaying and conveying statistical information. So as you can see in the introduction, this is what's known as an R Markdown document for .rmd file. Markdown is a format that's been used on the web for several years now, and it's very popular. You can go to this URL to see more information about the Markdown syntax, but if you just need a quick reminder, you can click on the question mark and then Markdown quick reference, where you can see in the bottom right window most of the commands and syntax that you would need in order to use this effectively. So putting emphasis, making lists, putting links and images, quotes. Most important is the R block quote, which we'll show some examples of below. It is 3 backticks and then R surrounded in braces, whatever your R code is, and then a line with 3 more backticks. That means that R code will be executed and the results will be displayed when you compile your RMD file into a PDF, HTML, etc. As a side note, we don't have homework this week, but when we do, the way to do it is to create a Markdown file that has your R code and then compile it to a PDF and upload both of those to Courseworks. To create a Markdown file, you can click on File and then New File, R Markdown. It will pop up this where you can put in a title and your name. You want to change this to PDF so that when you compile it, it becomes PDF. And you can upload both your RMD and your PDF file to Courseworks to turn in your homework. So last week we talked about the choose and the factorial functions. Both of those are available in R, and we can investigate those more closely. So here is a chunk of our code. If I wanted to execute that chunk, I could click on chunks and then run current chunk. In this case, I just want to run the single line, which can be performed by putting your cursor on that line or by selecting the entire line or the section that you are interested in. And then you can click on the run icon, which will also show you what is the shortcut under your operating system for piping a line of code from a RMD file or a .r file into the R interpreter below. So for me, that's Control Enter. When I execute that particular line of R code, it tells me the arguments to the choose function, which are n and k. And that makes sense because the choose function is defined as n factorial divided by k factorial, also divided by n minus k factorial. So we can verify that this would work in a simple case where n is equal to 3. So there n k is equal to 2. So there are 3 ways to choose 2 elements without replacement of a set of 3. In other words, there's 3 ways that each of the 3 elements could be excluded, leaving the other 2 included. If we execute choose 3 comma 2, we see that there are 3 combinations. We could do this the long way using the factorial function. Factorial of 3 divided by factorial of 2, also divided by factorial of 3 minus 2, which is just 1. Or if we really wanted to do it the long way, we could multiply out these numbers by hand. 3 times 2 times 1 divided by 2 times 1 times 1. In all 3 cases, we get the same answer, 3, which was the answer we were expecting. However, since the choose function is already available, you should use it whenever it's necessary rather than factorial or manual multiplication. We also talked about the binomial probability function, and this is also implemented in R. The formula for that, again, was n choose x multiplied by p raised to the power of x multiplied by 1 minus p raised to the power n minus x. R already knows that function and has a function to compute such probabilities, which is known as the d-binom function. It has 4 arguments, and if we executed help binom at this point, we could see the help page for the binomial density function as well as a few other functions that are related to the binomial distribution. In brief, these 4 arguments are x, which are the elements of the sample space whose probability you want to obtain, size, which is the total number of independent trials, which is what we referred to as n last week in lecture, prob, which is the probability of success in each independent trial, which we referred to as p in lecture, and log, which is an argument that defaults to false. However, if you explicitly set it to true when you call the d-binom function, it will return the logarithm of the probability that the random variable is equal to x rather than the probability itself. If you specify log equals false explicitly or don't specify anything about the log argument, then it will just return the plain probability that the random variable is equal to x on the 0-1 interval. In some circumstances, which we'll talk about later in the semester, it would be preferable to set the log argument to true to have better numerical stability. But for this week, we're not going to worry about it. We could verify that the d-binom function works in the sense it produces the probability that you obtain x successes and n trials when the n trials are independent by calling the d-binom function. Here we're going to investigate the probability that x is 2 when the number of independent trials is 4 and the probability of success on each independent trial is 1/3. If we execute that in R, we see that the probability is approximately 0.2963. We can verify that d-binom is producing the calculation we expect by calculating the probability under the binomial distribution manually with 4 choose 2 times 1/3 raised to the power of 2 times 1 minus 1/3 raised to the power 4 minus 2. Again, we get the same answer, and that was just an exercise. If you ever need to use the binomial distribution, which you probably will because it's extremely common in the social sciences, you should just use the d-binom function. Last week in lecture, we spent a considerable amount of time considering the distribution of pins knocked down in a frame of bowling under the binomial distribution, which is perhaps not very applicable because the pins are not independent of each other, but it's close enough for us to do some simple exercises to help understand probability and to understand how to do things in R. So in lecture, we asserted that the probability of knocking down each pin is 2/3, and there are 10 pins available to be knocked down on the first roll. On the second roll, the number of pins available to be knocked down depends on the realization of what happened in the first roll. And so to obtain the joint probability distribution, which in this case only has 2 events, so we refer to it as a bivariate probability distribution, the probability of knocking down x1 pins on the first roll and then knocking down x2 pins on the second roll, we use the general multiplication rule, which is said here in LaTeX code, but can just be explained as the marginal probability of knocking down x1 pins on the first roll multiplied by the conditional probability of knocking down x2 pins on the second roll, given that x1 pins were knocked down on the first roll. So we can construct this in R the same way that we did in lecture. So if I select this entire chunk, we're going to set the probability of success is 2/3. We'll set up our sample space omega as all the consecutive integers between 0 and 10. That's what the colon operator does. And then this next chunk of lines is going to apply to each element of omega the following function, denoting each element of omega by x1. We're going to return the marginal probability of knocking down x1 pins on the first roll because there are 10 pins available and each gets knocked down with probability p. Multiply that by the conditional probability of knocking down each element of omega that number of pins when the number of possibilities is equal to 10 minus however many pins were knocked down on the first roll. Again, each pin is knocked down with probability p. If I put that entire chunk and select it and pipe it into R, we see that the object joint underscore PR is an 11 by 11 array because there are 11 elements in our sample space. Because we have correctly used the rules of probability, all these joint probabilities together should sum to 1 by construction, and in fact, they do. We can now take a look at some of these joint probabilities rounded to 3 decimal places. So if we look at this matrix, this tells us for a particular row in a particular column, the probability that this number of pins is knocked down on the first try and this number of pins in the columns is knocked down on the second try. In other words, the probability of knocking down 5 pins on the first try and 3 pins on the second try is 0.045. The probability of knocking down 8 pins on the first try and 2 pins on the second try is 0.087, etc. Now, some of these in the lower right have probability 0 because they are impossible. For example, it's impossible to knock down 9 pins on the first try and 7 pins on the second try because that would be a total of 16 pins and there's only 10 available. However, some of these that appear to be 0 are actually positive, but rounded to 3 decimal places, they look like 0. Now, given this array of probabilities, there are several questions that you could answer in R. 1, what is the most probable result of 2 rolls in a frame of bowling? 2, what is the probability of getting a strike? 3, what is the probability of getting a spare, which is to say 2 rolls that add up to 10 pins knocked down, all 10 pins knocked down, excluding a strike, which knocks down all the pins on the first roll, and you don't even really get to do the second roll. 4th, what combinations are impossible due to the fact that you can only knock down 10 pins. So you should pause the video now and see if you can answer each of those 4 questions. To do this in R, if we go to the first question, what is the most probable result in 2 rolls? We can see by inspection that the most probable result is the one that has the highest probability. That is knocking down 7 pins on your first try and 2 pins on your second try, which has a probability of about 0.116, which is higher than any other possibility, although it's still not that large in absolute terms. We could get that programmatically by doing max of joint PR, which tells us this element. We could also use the which max function with the argument true, which tells us that is the 30th element of this 11 by 11 array is the one that has the maximum value of joint PR. So that would be 11, 22, 23, 24, 25, 26, 27, 28, 29, 30. Again, that is the most probable result, knocking down 7 pins on your first try and 2 pins on your second try. Question 2, what is the probability of getting a strike? That is the event that you knock down all 10 pins on your first try, and you can say 0 pins on your second try, even though you don't even do the second roll. So that probability is approximately 0.17 under the data generating process that we have created. Excluding a strike, the probability of getting a spare is all the other elements in our joint probability table where the sum of the number of pins knocked down on 2 rolls is equal to 10, excluding a strike. So that would be the event that you knock down 9 pins on your first try and 1 on your second try, 8 on the first try, 2 on the second try, 3 on the, or 7 on the first try, 3 on your second try, 6 and 4, 5 and 5, 4 and 6, 3 and 7, 2 and 8, 1 and 9, and 0 and 10. Since these events are disjoint, the probability of one or the other of those 9 possibilities happening is the sum of all those probabilities. That follows from our general addition rule. So in your head, you could go and add up all these results, but we can do this more programmatically in R by using index operations. So in order to refer to a row and a column, you can do so by name. This is a bit confusing in this particular case because the rows are named starting with 0. So we don't want to refer to the 9th row because 9 actually corresponds to the 10th row in our 11 by 11 array. And thus we have to use the quotation marks to refer to the row named 9. If we didn't have the quotation marks, it would refer to the 9th row, which is actually the event that 8 pins are knocked down. Similarly with the columns, we can select the first or the row named 1, which is actually, or the column named 1, which is actually the second column because the first column is the event that you knock down 0 pins. So if we just add up all these combinations, so 8 and 2, 7 and 3, 6 and 4, 5 and 5, 4 and 6, which is a different event than knocking down 6 pins on your first try and 4 on your second try, 3 and 7, 2 and 8, 1 and 9, and finally 0 and 10. So the sum of all those probabilities is the probability of getting a spare, but not a strike, and that is about 0.29. Which combinations are impossible? Those are the ones where the number of pins allegedly knocked down on the first two tries exceeds 10. So those are the ones basically in the bottom right corner. We could test for that programmatically by looking for the number of elements in joint PR where the probability is exactly 0, and that is 55 of the 121 cells in our joint PR array. So hopefully you got those questions right. Moving on. The next thing we want to go over again, in lecture we obtained the marginal probability distribution of the number of pins knocked down on the second roll by taking our set of joint probabilities and summing over all the bivariate probabilities that involve knocking down x2 pins. So for example, if we're interested in the probability of knocking down 4 pins on the second try, we would take the event knocking down 0 on the first try, 4 on the second try, add that probability to the probability of knocking down 1 on the first try, 4 on the second try, 2 on the first try, 4 on the second try, etc., all the way down to 6 on the first try and 4 on the second try. Once we get to this row of column labeled 4, it's not necessary to continue on to the event 7 pins knocked down on the first try, 4 pins knocked down on the second try, because that would be 11 pins knocked down, which is impossible. However, because these events are assigned probability 0, we can just sum all the numbers in the column labeled 4 in order to get the probability of knocking down 4 pins on your second try marginally, which is to say irrespective of how many pins were knocked down on your first try. To do this for all the possibilities of things that could happen on the second try simultaneously, we can execute this line in R, which gives us a vector of length 11 for all those probabilities. We could look at those, again, rounding to 4 digits or so. The probability of knocking down 1 pin on the second try over all the possible things that are consistent with that could have happened on the first try is 0.23, and that is reasonable because most of the things that could happen on the first try entail only a small number of pins available to be knocked down on the second try, and so essentially averaging, we get a smallish probability there. We can look at these results graphically using a bar plot. This first line is the guts of the plot that I'm about to show. The second line is only for formatting the plot, and adding decoration is less essential. So you see that plot appear in the bottom right. You can click on zoom, and I don't know if this will appear on the video, but if it does, we have a bigger plot here, which shows the probability for each of the possibilities in our sample space, the probability of knocking down that number of pins on the second roll. The most likely is 2, because it has the most probability. So we say that is the modal category. 1 and 3 have about the same probability, and it declines thereafter. So it's important to realize that this probability distribution for the number of pins knocked down on the second roll is a well-defined set of probabilities, but it's not a probability distribution that has any special name. There's no function that you can call in R to utilize it. It's something that we constructed by multiplying a marginal probability of knocking down x1 pins on the first try times the conditional probability of knocking down x2 pins on the second try, given that you knocked down x1 pins on the first try, and then summing over the columns of our joint PR matrix in order to get probabilities irrespective of what happened on the first try. That is to say, the marginal probability of knocking down x2 pins on the second try. But that marginal probability distribution, although useful and entirely valid, is not something that has any name. It's just the marginal probability of knocking down x2 pins under the data generating process that we've assumed. Once we have the marginal probability distribution for knocking down x2 pins on the second try, we can go on to calculate the expectations of common functions in probability. We presented the formula for calculating the expectation of a function in lecture. It is the sum over all the elements in the sample space of the function that you're interested in multiplied by the probability that that element of the sample space occurs. So in the case of the expectation, we're simply using an identity function for g of x equal to x. So for each element of omega, we multiply that by its respective probability, sum over all of those, and that creates the expectation of x2, which we're going to save by assigning it using the arrow operator, and we're going to print it to the screen by including the whole thing in an extra set of parentheses. And we see the expectation for the number of pins knocked down on the second try is 2.2 repeating, irrespective of how many pins were knocked down on the first try. We can then calculate the variance of the number of pins knocked down on the second try by using a slightly different g function. Here we're using the function x minus mu quantity squared. We're taking each element of omega, subtracting its expectation, squaring that quantity, and scalar multiplying by the probability of each of the elements in the sample space occurring on the second roll. The variance is a measure of how spread out the distribution is, and when we pipe that into R, we see it's 1.7284. In contrast, we can recall that the marginal variance for the number of pins knocked down in the first try under a binomial distribution is n times the probability of success times the probability of failure, which is 2.22. Thus, the variance on the second roll is smaller than the marginal variance on the first roll, and that's again due to the fact that there's fewer pins available to be knocked down on the second roll than there is on the first roll. Another measure of the spread of a distribution is the standard deviation, which is not an expectation, rather a function of an expectation. The square root of the variance is the standard deviation, and it's a more popular measure of the spread of the distribution. It is stated in the same units as x, whereas the variance is stated in squared units. We can calculate the skewness of the distribution for the number of pins knocked down on the second attempt by using a slightly different g function. This is the function x minus its expectation divided by its standard deviation, that quantity raised to the power of 3, and then multiplied by the probability of each element in the sample space occurring, summing over the entire sample space. So what does skewness tell us? If x is less than 1 standard deviation from its mean, then subtracting the mean and dividing by the standard deviation will result in a number that is closer to 0, but in any event is between 0 and 1. When you take a number that's between 0 and 1 and cube it, it gets even closer to 0. However, if some element of omega were more than 1 standard deviation away from its mean, this function in parentheses here is going to be greater than 1, and when we cube it, it becomes much greater than 1 at a pretty fast rate. Conversely, if some element of x were at least 1 standard deviation below its expectation, then you would have a number that is less than -1 being cubed, and that is going to become a much more negative number at a fast rate. When each of those numbers are weighted by the probability they occur, so extreme events with low probability are downweighted, and we sum all that up, if the skewness is positive, that's basically to say we expect the standardized version of the random variable, which is to say x minus its mean divided by its standard deviation, to be positive. And if the skewness is negative, then we expect that number to be negative. In this case, the skewness is positive, which is perhaps suggested by this picture of having a long tail of the probability getting up to 10 pins knocked down on your second roll. Excess kurtosis is a similar function. Again, you standardize by taking the random variable minus its expectation divided by its standard deviation, this time raised to the power of 4, which is an even more extreme function before you weight by the probability of each event in the sample space occurring. Sum over all that. The excess kurtosis subtracts 3. 3 is the raw kurtosis of the normal distribution. So by subtracting 3, we get excess kurtosis relative to the normal distribution. And a bigger value of excess kurtosis means that the distribution being considered here would have more peakedness than a normal distribution. In this case, the excess kurtosis is slightly negative, indicating that it has about as much peakedness as a normal distribution, but a little bit less. We will talk about the normal distribution on Tuesday. Finally, another function that we're interested in is the negative of the logarithm of the marginal probability. That's our G function. We multiply by the marginal probability of each element in omega happening, sum over all that to get what's known as the entropy. Now you can show that the maximum entropy is achieved for a discrete uniform distribution. So that would be a distribution for something like the roll of one die. It can be the numbers 1, 2, 3, 4, 5, 6, each with probability 1/6. So when all the elements have the same all the elements of your sample space have the same probability for a discrete distribution, that is a discrete uniform distribution, and that maximizes the entropy. Thus, when we calculate the entropy for another distribution, such as this one, in this case, the distribution for the number of pins knocked down on the second roll, we can compare that to the entropy for a discrete uniform distribution in order to tell us how close is the distribution under consideration to a uniform distribution. You can see from the picture that the probabilities of each of these events are somewhat different. So this is clearly not a uniform distribution, but we can quantify how close it is to a discrete uniform distribution for a sample space that has 11 elements by calculating the logarithm of 11, which is the entropy that would be achieved for a discrete uniform distribution with 11 elements in its sample space. And we can see that the entropy of the distribution of the number of pins knocked down on the second roll is about 2/3 or so of the maximum possible entropy that could be achieved when the sample space has 11 elements. Moving on, it makes sense logically in terms of the substantive application to bowling to think of the bivariate probability distribution as being generated by a marginal probability of knocking down x1 pins on the first roll multiplied by the conditional probability of knocking down x2 pins on the second roll, given that you knock down x1 pins on the first roll. However, from a logical perspective or a mathematical perspective, it's just as correct to reverse the order and think about the bivariate probability of those two events as the marginal probability of knocking down x2 pins on the second roll times the conditional probability of knocking down x1 pins on the first roll, given that you knock down x2 pins on the second roll. Now, that might not seem particularly realistic, but it is mathematically correct. One way to get some intuition about it is imagine that you go into a bowling alley and someone is jumping up and down saying, yay, I knocked down 3 pins on my second roll. What would be the probability distribution for the number of pins that that person knocked down on the first roll, which you didn't see because you were still, getting your bowling shoes or whatever. So we can construct this conditional probability distribution for the number of pins knocked down on the first roll, given however many pins were knocked down on the second roll in R, by dividing the bivariate probability distribution by the marginal probability distribution of knocking down x2 pins on your second roll. So this can be accomplished with the sweep function. Recall that joint PR is a 11 by 11 array that looks like this. So what the sweep function does is it takes its argument, which in this case is joint PR. It goes over one of the margins of an array, in this case the second margin, meaning it's going to sweep over the columns. It's going to use the statistics, the 11 elements of the vector PRX2, which is the marginal probability of knocking down x2 pins on your second roll, and it's going to apply the function division. So basically, for each column in joint PR, it's going to divide that column by the corresponding element of PRX2, that being the probability of knocking down x2 pins on your second roll. Because the bivariate or joint probability is the product of a marginal probability and a conditional probability, a joint probability divided by a marginal probability yields the corresponding conditional probability distribution. In this case, the probability of knocking down x1 pins on your first try, given that you knock down x2 pins on your second try. So we can pipe that into R and verify something that mathematically has to be the case, that this conditional probability distribution, because it's a valid probability distribution, it's going to sum to 1 for each element of the corresponding matrix. So again, PRX1 is going to be an 11 by an 11 array. We can look at that briefly. So within each column, these probabilities are going to sum to 1. So what this tells you is, given that 2 pins were knocked down on the second try, what is the probability that a certain number of pins were knocked down on the first try? You can see these numbers, although they look like 0, are slightly positive. It increases, and then, it decreases once you get to 8 pins knocked down on the first try. And then 9 and 10 are exactly 0, because given that you knocked down 2 pins on your second try, it's impossible for you to have knocked down 9 pins or 10 pins on your first try in that frame. So if we want to look at the fifth column, which is the probability of knocking down a certain number of pins on your first try in the frame, given that you knocked down 5 pins on your second try of the frame, we can pull that column out using the extraction. So we did that operator before when we were counting the probability of getting a spare. If you don't put anything in the first space and then just comma and a row and a column indicator in the second space, it's going to pull all the elements of the designated column, in this case, the fifth one. So again, you can see these numbers match up with these numbers here, and all the ones 6 or greater have probability 0 because you can't knock down that number of pins on your first try, given that you knocked down 5 pins on your second try, because the total would exceed 10 pins. So if that is the probability distribution conditional on knocking down 5 pins in your second try, we can do some exercises. If x2 plus 1 is the month that you were born in, excluding those of you who were born in December, in which case you can just imagine that you were born in June, what is the conditional mean, the conditional variance, the conditional standard deviation, the conditional skewness, the conditional excess kurtosis, and conditional entropy of the number of pins knocked down on the first roll, given that you knocked down x2 pins on the second roll? And for the entropy, in order to do this question, you're going to want to pass the argument na.rm equal true to the sum function, because for entropy, you may end up in a situation where you have 0 multiplied by the logarithm of 0. Since the logarithm of 0 evaluates to negative infinity, R thinks you're trying to multiply 0 by negative infinity, which is not defined, so it will return NA for those elements. However, the limit of x times the logarithm of x as x approaches 0 from above is 0. So by continuity, we define 0 times log 0 as being equal to 0. And by excluding the NAs, you basically treat those as being 0. So this is going to entail selecting the appropriate column of the PR x1 given x2 matrix, depending on what month you were born in, using that as the conditional probabilities to use in the calculation of the expectation of these functions, just like we did above when we were calculating the expectation of various functions of the number of pins knocked down on the second roll. Here we want to calculate the expectation of various functions, the number of pins knocked down on the first roll, given that x2 pins were knocked down on the second roll, given that x2 plus 1 is the month you were born in, unless you were born in December. So you should pause the video now to see if you can obtain those conditional expectations. So to do this in R, I was born in August. So if x2 plus 1 is 8, then x2 is 7. And I will just calculate this as extract out the column labeled 7. So I'm interested in the event that 7 pins were knocked down on the second roll. What's the probability distribution for the number of pins knocked down in the first roll? And then to calculate the expectation, variance, etc., we can do something like this. Is the sum of omega times ERX2 7. And again, we'll put an extra set of parentheses to not only save that, but also to print it to the screen. So the conditional expectation for the number of pins knocked down on the first try, given that 7 pins were knocked down on the second try, is 2.57. Similarly, we can calculate the variance by considering a slightly different G function. Here we're going to subtract the conditional mean from each element of the sample space, square that, so that's our G function. Again, weight it by the conditional probability, sum over the entire sample space, assign that to a object, and print it to the screen. In this case, the variance is 0.367, which is very small relative to the marginal variance, which again was 10 times the probability of success times the probability of failure. That is the marginal variance for the number of pins knocked down on the first roll, in contrast to the conditional variance of the number of pins knocked down on the first roll, given that 7 pins were knocked down on the first roll. We can calculate the standard deviation as the square root of that variance, as always. Then we can calculate the skewness need some more parentheses here. So that is the function x minus its mean divided by its standard deviation, all cubed, weighted by the conditional probabilities, summed over the whole sample space. And we can see now we have negative skewness, whereas I believe before we had positive skewness. We can calculate the excess kurtosis similarly, just by using fourth power here instead of third power, and then subtracting 3 from the result in order to get the kurtosis relative to the normal distribution, which in this case is positive, indicating this conditional distribution has more peakedness than a normal distribution, which we will learn about on Tuesday. Finally, we can calculate the entropy using negative log PRX to 7. And as I was mentioning before, we want to pass the NARM as true argument to the sum function in order to exclude those. And we see that there's less entropy or not very much entropy relative to a discrete uniform distribution for this distribution on the number of pins knocked down on your first try, given that 7 pins were knocked down on your second try. So that's how we can calculate expectations. If we want to calculate conditional expectations, all we have to do is use the same G functions that we have learned about, that whose expectations of those functions have special names, but using conditional probabilities rather than marginal probabilities as the weights, as we sum over the evaluations of those G functions over the entire sample space. Now we can move on to talking about the Poisson distribution, which, as we talked about in lecture, is a distribution for counts. the probability of a count being a particular number. Again, R already has a function to calculate those probabilities. It's called the dPois function. Its arguments are very similar to the arguments for the dbinom function. If we did help of that, we could see in more detail what these arguments are. But briefly, X is the elements of the sample space whose probability that you seek. Lambda is the parameter of the Poisson distribution, which, as we talked about last week, is the expectation and the variance of the Poisson distribution. And logarithm is the same idea as in the dbinom function. You could set that to true in order to obtain the logarithm of the probability, but we're just going to leave that alone in order to obtain the regular probability between 0 and 1. In the case of a count, there's no upper bound on omega, so it has an infinite number of elements. And because it has an infinite number of elements, we can't simply enumerate those probabilities. However, for small values of lambda, the probability of getting a really big count, like 1,000,000 or something like that, is negligible because the mean of the distribution is going to be some small number like 3, and the variance of the distribution is going to be that same number, 3 in this case, and thus the probability of getting a number like 1,000,000 when the mean and the variance are 3 is extremely small and so close to 0 that it's essentially negligible. So if I just use the same finite number of elements that I had before, 0 through 11, and calculate the sum of those probabilities under a Poisson distribution, we see that those 11 elements of the sample space constitute 0.9997 probability that one of them occurs. And so the probability that getting any number greater than 11 under this data generating process would be 1 minus that number. And that is spread out over all the integers 12, 13, 14, up to infinity. As before, we can visualize these probabilities using a bar plot. The first part is the guts of the function. The second is just decoration of the axes and label names, etc. So we can see this plot here, the counts of the probabilities. So the probability of getting 2 or 3 is about equal. There's some probability of getting 0 or 1. After 3, it starts declining pretty quickly, and thus you can barely see in this chart the probability of getting a count of 10 under a Poisson distribution with a lambda of 3. If we go back to our file, we can ask the last exercise question for today. What is the probability of a count being less than or equal to 6 under a Poisson distribution with a rate parameter of lambda equal 3. So you should pause the video now to see if you can use R to answer that question. In order to answer this question, we simply take the probabilities under a Poisson distribution for the first 7 elements of omega, or we could just put in again 0 to 6, and using the parameter lambda that we had specified before, summing those probabilities. Because these events are disjoint, you can't get a count of both 4 and 2, so there's no correction we need to make for the probability of both of them occurring, because the probability of any 2 disjoint events occurring is 0. So this is essentially the probability of getting 0 or 1 or 2 or 3 or 4 or 5 or 6. And the general addition rule tells us that in the circumstances like these, we can just add up the probabilities. So when I enter that into R, we get a 0.96 6 probability of the count being less than or equal to 6. Conversely, a probability of 1 minus that for the probability of obtaining a count greater than 6. So the last thing that I want to show you is that when you're doing your homework and you're finished, you have an RMD file that has explanations in English. You can use a little bit of LaTeX if you know it, but you don't have to. You can certainly explain the intuition of your answers without that. But when we click knit PDF, it is going to take all of those code chunks that we defined in our RMD file, execute the R code, and output the results underneath each R chunk in a PDF file, do some syntax highlighting, etc. So it's pretty easy to read. And it will create a PDF full file in the folder in which you saved your RMD file. So in this case, I can open that file that I just created and get a PDF of everything that we just went over. So we can see back at the beginning, we asked what are the arguments to the choose function. In the outputted PDF, it's going to highlight that in gray to emphasize that it's R code, highlight the function name, etc. And then underneath it, we'll put the output of executing that R code also into the PDF after pound signs to indicate that it is our output. So you can see it did that for each of the things that we did when we created a plot. It comes out underneath the code that generated, etc. And so we have reasonably nice looking document where we have our code, we have our output, and we have our explanations and interpretations of that code and output all assembled together in a format that's not quite publication quality, but is good enough for the purpose of our class for turning in homework. So when we have the first homework assignment next week, what you'll need to do is create a .rmd file that has your English explanation, your R code, and then knit that by clicking on knit PDF. It will make the PDF that gives everything a nice format, and then upload your RMD file and the PDF file that it generates to Courseworks in the assignment section. So that is it for this week.